The idea of color correction and filtration is a concept that we need to understand to work in film and video production. The reason being is that sometimes when we're on locations, we may have to work with a certain type of light source, like fluorescence or like daylight coming through a window. And those types of sources, all the different sources in the world, can produce a very different color of light. We refer to color temperature or the Kelvin scale and the Kelvin temperature of the light. What that means is the whiteness of the light, how much red, green, and blue is present to make it a very full spectrum light. So sometimes we have what may be a very, very orange light, and we need to alter that and bring that more toward the blue scale if we're working with daylight, for instance. Daylight is a very, very blue color light relative to television, or what we call tungsten lights. So if we're mixing the two, we either need to correct with gels the tungsten light and bring it toward the color of daylight, or correct the color of daylight, this very blue light, and bring it toward the warm orange color of tungsten lights. So we use different gels and filters to correct different types of sources on location, usually, to make these all of these sources mixed together into one very full spectrum of what we'd call white light. Now, the understanding of Kelvin scale and the manipulation of which gels to use is something that takes a little bit of understanding and also takes some time to learn to see which things work best for different types of film stocks and in different situations. But once you get the concept down, then there are very few situations that you'll find yourself in where you don't know which way to turn. You have an idea of which type of source this is, what color it generally is, and how you need to work with gels and filters to alter that color to get your best effect on location.
The human eye is sensitive to only a very narrow region of light called the visible light spectrum. Above and below this spectrum is light that cannot be seen by the naked eye. This visible wavelength spectrum, which is rated in nanometers, or billionths of a meter, represents the scope of light that we work with in film and video production as well. When all colors of this visible spectrum are present, we call this white light. The eye perceives nearly all light as white light. Our eyes will automatically adjust for any deviations in color balance. But a video camera or film stock cannot compensate for the lack of any certain color of light. We must compensate through color correction. If we heat a piece of black metal hot enough, it will begin to glow. Beginning first with a warm red-orange glow, more electrical energy can be forced through a metal filament, and it gets brighter. As the energy is increased, the color of the light changes toward a cooler and whiter color. This visible heat is the basis for incandescent lighting, or the common light bulb. To measure the true color or whiteness of a light source, the Kelvin temperature scale was developed by 18th century physician Lord Kelvin. The color temperature of a source refers to the balance of color or the amount of red, green, and blue light that is radiated by a source. Simply put, the lower the color temperature, the warmer the color output of the source. The higher the color temperature, the cooler the color output. This color of light that is emitted by a light source can be called the spectral distribution of light. Incandescent sources, such as those used in our home, actually emit a very red-orange color of light, which registers at approximately 2800 degrees Kelvin. Although they are considered a white light source, because all colors are present, much more red and orange light is emitted than any other color. Standard tungsten lighting fixtures produce a similar but slightly cooler color of light at 3200 degrees Kelvin. The midday sun, which radiates a bluer and more even spectrum of light, is rated at approximately 5600 degrees Kelvin and is also considered a white light source. Depending upon the time of day, the weather, and other factors, the color temperature of daylight can range from 4,000 or 5,000 degrees to over 20,000 degrees Kelvin. A look at this professional fluorescent tube fixture demonstrates how a video camera or film stock will record 2 tungsten and 2 daylight color temperature bulbs. In this shot, with the camera set to record the color of daylight, the daylight-colored bulbs appear white, while the tungsten bulbs appear a warm orange color. With the camera set to record the color of tungsten light, the 2 tungsten bulbs now appear white, and the 2 daylight-colored bulbs appear quite blue. We can clearly see that the camera cannot see both color temperatures simultaneously as white light. It is for this reason that we sometimes must modify or correct the color of a light source to match either existing light conditions or other light sources.
There's a couple of important facts that you should understand about working with gels and filters. And the first, especially about gels, is that when you put a gel on a light, it does kind of the opposite of what you might think it'll do. For instance, if we put a blue correction gel on a tungsten light, it doesn't add blue light. It subtracts all the opposing or complementary colors to leave only that blue light to pass through. Someone once told me of an analogy of adding a filter to your water faucet at home. You're not adding good water. You're subtracting all the bad, unwanted particles out of that water to make it taste better. So gels and filters do the same thing. They subtract the opposing, the unwanted colors and leave only that color that the gel is. For instance, a green gel, you're subtracting all the other colors and allowing only green to get through. Now, the other thing you need to understand about gels and filters is that while you're subtracting all those other colors, is that you're also losing some of your light value. So a lot of gel swatches will have listed what you'd call a transmission factor. How much light gets through this gel? How much am I losing? So a particular gel might list a transmission of 25%. And what that means to you is that if you start out with a 1,000 watt light and put this gel on it, you're only going to end up with 250 watts of light, 25% of that light value. So what you need to factor in when you're using certain gels is that, gee, if I wanted that 1,000 watts of output, I need to start with 4 times more light. I need to start with 4,000 watts of light. Then when I only get a 25% of it, I'll end up with that 1,000 watts that I need. So this whole idea of the complementary colors being absorbed, etc., and the fact that you do lose light value as well is something that's important to understand about using gels.
To understand how to utilize the many gels available to you, you must first understand how gels are designed to help you. A look at a page from the GAM Colors Swatch Book shows that several different points of information are provided for the user. Printed at the top are the company's gel number and a listing of the particular gel name. In this case, the color correction gel called half CTO, or 1/2 color temperature orange. Below the gel name is the Kelvin temperature shift value. Using this gel to correct a light source will shift the Kelvin temperature down on the temperature scale by approximately 1700 degrees. That means that the source will appear 1700 degrees Kelvin warmer by using the gel. This is an approximate rating due to the fact that the degree of Kelvin shift will differ depending on the Kelvin temperature of the original source. Just above the graph is the transmission factor, a listing in percentage points that tells us the total transmission of light through the gel. This CTO gel transmits 73% of the visible light and absorbs 27% of the opposing colored light. Half CTB correction gel transmits only 44% of the total light value. This loss of light due to the use of any gel is an important factor to consider when selecting an instrument or calculating an exposure. Below all of these numbers is a graph, which plots the spectral distribution of the gel. This means that the graph shows which wavelengths or colors of light are absorbed and which are transmitted through the gel. At the left of the graph is the transmission percentage, and at the base of the graph is a nanometer scale. By comparing the graph with the color chart provided at the front of the swatch book and looking at the transmission factor and Kelvin shift, you can accurately predict the effects that each gel will have on a light source.